This is Lecture 5C for Calculus 1 on Riemann integration. There is a parallel between Riemann integration and integral calculus, and this is parallel to the slopes of secant lines and differential calculus. Here was the situation in the development of differential calculus. We wanted to compute the slope along an arbitrary curve, but we didn't know how to do it. We did know how to compute the slope of a straight line. So we used what we knew how to do and approximated the slope of the curve at a particular point by the slope of a straight line. Then we refined the straight line approximation by choosing points that were closer and closer together. Then we took the limit and called that limit the slope of the curve at that particular point. After that, we used algebra to derive a function for the slope of the curve in general. This replaced that numerical method and that graphical method of drawing straight lines and taking limits. Then we abandoned the word slope in favor of the word derivative, although slope is sometimes still used, and then the derivative assumed a life of its own. And I'll look at the situation for the development of integral calculus, and you'll see it's exactly parallel. Here's what we do to develop integral calculus. We don't know how to compute the area between an arbitrary curve and the x-axis, but we do know how to compute the areas of rectangles. So here we go again. We approximate the area beneath the curve with the area of rectangles. Then we refine the approximation by using more and more rectangles, making them thinner and thinner, closer and closer together. We can't make them infinitesimally close together, so we take the limit, well, as they become infinitesimally close together, we take the limit and we call it the area under the curve. Now we're going to use the fundamental theorem of calculus to dispense with all this rectangle drawings and write the area under the curve in terms of the primitive of the functions. Again, just like with differential calculus, drawing secant lines got replaced by formulas for taking the derivative. In this case, drawing rectangles gets replaced by the primitives of functions, by the integrals. Okay, at this point we abandon the word area in favor of the word integral, although area is still used in some situations, and then the integral assumes a life of its own. So, exactly parallel. And for those of you in physics who are searching for symmetry often, this parallel is a form of symmetry. So now I'll describe Riemann integration. We're going to consider a function that is continuous and has at most a, I'm going to say, finite number of jump discontinuities. In the book, they say the function has to be continuous, but that's not necessarily true. It can be extended to having a certain number of jump discontinuities, and that's a lot of work in math to determine how many jump discontinuities you really can have. So I'm just going to say a finite number. All right, and let's consider this function only on the interval, closed interval AB. Right, for convenience now we're going to assume that f is greater than 0 for all x in AB. We're going to approximate the area between the function and the x-axis by creating a tag partition of the graph. The word partition, or mesh, you can use the word mesh too, means that the interval between a and b is subdivided into smaller subintervals. If we break it into 100 small intervals, the size of each small interval I'm going to call delta x. It's going to be b minus a over 100. The tag part of tag partition means that each rectangle or each little subinterval is tagged with a value of the function at some point in the subinterval. I'm going to call that f of x star. X star is a value of x in a subinterval. This value is going to represent the height of the rectangle. Although you could get very clever, there are actually 4 choices for the location of the height. You could put it on the left-hand side of the rectangle, on the right-hand side of the rectangle, or in the middle. You can also take it as the average value of functions near the rectangle, but we're only going to consider the first 3, left-hand side, right-hand side, middle. And I'll show you now what that looks like. You've seen it before. here's a curve in red. That's the function we want, and we want to find, disregard that the x for the minute is way down here. That just, I drew it like that to get the numbers out of the way. But I'm only going to consider the function between x equals 0 and x equals 4. So my a is 0, my b is 4. I create my partition, or my mesh is pretty coarse. It has just 4 subintervals in it. Right. Then on each subinterval here, 3 to 4, I look up here and I grab the value of the function at the left-hand side. And that is the height of this rectangle. Over here's my second subinterval. I go up to the function and grab that height at the left-hand side of the rectangle. Now I've got a rectangle. Same here. And then, of course, at this side it's 0, so that's that. Here is the same function, the same curve, and the same partition, but now I am using the right-hand values for f of x. So on this interval, I went up here and I grabbed the value of the function on the right-hand side, and that created me this rectangle. For the subinterval between 2 and 3, I went up here on the right-hand side and grabbed the value of the function. That created this rectangle. Notice these are a little bigger than the function. Okay, that will be taken care of. Between 1 and 2, I go up and grab the one on the right-hand side, and I get this green one. Now for 0 to 1, I go up here and grab the value on the right-hand side, which is not 0 in this case, and so I get this little blue rectangle. Here's the same situation, same partition, but now I'm going to use value of the function in the middle of the rectangle. In the middle of the in the middle of the subinterval 3 to 4, and this creates a rectangle. Here's the purple one. You can see now I've got the value in the middle between 2 and 3. Here's the the value in the middle between 1 and 2, and here is a value here between 0 and 1. So I think now you understand what I mean by partition. You take your interval AB, divide it into subintervals. In this case, they're all even. In advanced numerical methods on a computer, they would not necessarily all be even. But right now we're going to just let them all be even. Then you have to create little rectangles by using the value of the function. You can pick the function at the right-hand side of the subinterval, the middle, or the left-hand side of the subinterval. And then you get your rectangle. In the next step, you compute the area of each little rectangle. Then you add them all up, and you say that approximates this area. So an approximate area is this sum over all these little rectangles. And now you let the number of rectangles go to infinity. You let n, there's n, which is a number of subintervals. You let that go to infinity, and that limit is the area. That is Riemann integration. We can use the definition or the notation of the definite integral for Riemann integration. Here again is this notation. The area A under the curve equals the integral between A and B. A and B are the limits of integration. A is called the lower limit, B is called the upper limit. A does not necessarily have to be less than B. Okay, f of x, that's the curve. I'm taking this, computing the area underneath, and dx singles out the independent variable. It's actually a dummy variable of integration. The d means that size of the partition, which was delta x, meaning fairly large, crude partition, has become infinitesimally small. So we say in the limit that Riemann sum of rectangles becomes the definite integral and the area between the curve and the x-axis. And here is an example. Let's look at the parabola. F of x equals x squared, and we want to set a equal to 0 and b equal to 4, as in those graphs that I showed you a minute ago. We're going to create that partition of 4 subintervals, so the width of each subinterval is 1. We'll choose the height, right hand, left hand, and middle, and compare what we get. When I did that and added up the heights, I found that, remember here are those subintervals, 0 to 1, 1 to 2, 2 to 3, 3 to 4. Here's where I picked the right hand endpoints. Here was the left hand endpoints. And here I picked the ones in the middle. If I add just these 4 up, for the right hand endpoints I got an area of 30. For the left-hand endpoints, I got an area of 14. For the middle, I got a 21. The actual area is 21.3333b. Well, the middle looked pretty good, so you might say I should use middle. The idea here is not necessarily, because you're going to get these rectangles in the limit are infinitesimally small, so that the right hand, left hand, and middle are actually the same value in the limit. But it does look here like the middle would work. If you had a curve with, this curve is concave up. If you had a section of the curve where it was concave down, the fact that the right endpoint overestimated and the left endpoint underestimated, that would be reversed. You can imagine how those rectangles would fit into the curve. So instead of trying to figure out right, left endpoints or middle, generally, I don't know what I used to do. There's several numerical methods. You can just go ahead and pick them, and you're going to take the limit anyway. And in what you're using the integral, you're going to do this in abstract, and it won't matter. All this will vanish. Only be used in certain situations where you do not have an analytic method. So I'll show you again the rectangles. This is Riemann integration, right? I'm using the left-hand values of the function. Get the highlighter here. Here's the left-hand values of the function. Right? You see, I picked them on the left-hand side of the subintervals. The area of these rectangles is 14. The real area under the curve is 21 1/3. Here's Riemann integration again. Now I'm using the right-hand values. See, I picked the ones over here on the right at the edge of each subinterval. The area under the curve is 30, and you would guess that because the rectangles are sort of sticking out over the curve. They're bigger than the curve. Actual area again is 21 1/3. And here, using the middle values, and we got 21 and 21 1/3 was the actual area. So even with this crude partition, you can see that it works, and I think you get the idea that you'll let these, the number of subintervals increase, you will get a better fit to the curve. Now in the example above, the mesh was evenly spaced. That's not necessary, and it's not necessarily the best choice, especially if the function has discontinuities. Computers have algorithms that optimize the size of the mesh. Okay. The following is an example of a piecewise function of horizontal segments. So this is going to show you two things. It's going to show you a mesh that is not even. All right, and it's also going to show you that you could use Riemann integration if you have and I'll say finite number of jump discontinuities. You just have to put the edge of the mesh right at the discontinuity. And you've seen this before. This was that velocity calculation I did in the introduction. So here we have a piecewise function that's 60, 80, and then 37.5. Okay, if I wanted to use Riemann integration here, there'd be no reason to divide this section up into a whole bunch of rectangles. Just use one. And obviously this makes a rectangle itself, and so does this one. Now you want to put the edges of your mesh right at the discontinuity, then you don't have any problems. You can go ahead and use Riemann integration for functions that have jump discontinuities.